Good morning. Everybody. I'm going to give people just a minute or two to join, fix my hat. Good morning, good morning. Give people just one more minute to join us. All right, so I'm going to start. Thing won't stay. All right, let's start with a little recap. Dun, 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 dun. All right, let me share this screen with you. Okay, so a little recap of what we've been covering so far. So anytime a wave hits the surface, could be a sound wave, could be a water wave, could be light in this case. Three possibilities for what could happen. One, hold on a second, turned off. All right, let's choose a new color. Let's choose green. Okay, so three possibilities for what can happen when light hits a surface. One, that light can get absorbed. If an object absorbs light, light does have energy, so it's going to absorb the energy that that light had. Two, it can get transmitted. And we're going to look at this next chapter. It's called refraction. But when light goes from one transparent material to another, that light can bend. It can change the direction it's moving. And then it can also be reflected. So when is light absorbed? When is it going to be transmitted and reflected? It depends upon the frequency of the light compared to the natural frequencies of, in this case, let's say glass. If light matches an object's natural frequency, that light is going to get absorbed, because when what happens is light comes in, an electron in that first atom, and let's say glass, absorbs it. But since it matches one of its natural frequencies, it starts to oscillate very rapidly, runs into neighboring atoms, loses the energy as heat. If the light does not match one of the natural frequencies of, let's say, the glass, then that light is going to get re-emitted, and then there's two possibilities. It can get re-emitted along the same direction it was traveling, in which case it's transmitted, or it can basically be re-emitted but back the direction it came. And that's in essence what reflection is. So let's just say that this was a opaque object, so not a piece of glass, so this might be a shirt or something. What ends up happening, the way you see any opaque object, an object you can't see through, is by light shines on it. That opaque object is going to absorb most frequencies of light. It will reflect some frequencies back. The color of an opaque object is the same as the color of light that it reflects. So a red object appears red because white light is shining on it. It's absorbing some frequencies of that light. The frequencies that it reflects is the frequency of the color that you're going to see from that object. So if something's blue, that means it's reflecting blue light back to you. If it's red, it means it's reflecting red light back to you. And then we also talked about the visible spectrum. So visible light is just an electromagnetic wave within a certain frequency range that we as humans have evolved to see in. We generally break up light into low frequency, middle frequency, high frequency. Red, orange, yellow, these are all considered low frequencies. Green is sort of middle frequency, and then blue, indigo, and violet are high frequency. There is a specific frequency for each one of these colors, but white and black are not real colors in a sense. There's no frequency of black light. There's no frequency of white light. White is when we have all colors mixed together equally. So when we see all frequencies being reflected from something, we see that as white if there's white light shining on it. Black is basically the absence of color. So anytime we look at an object and there's no light coming from that object, we see it as black. So color of an opaque object is the color of the light that it reflects, or the frequency of it reflecting. And then one thing I mentioned is that a red object can only appear red if it has red light to reflect. So if I were to shine, let's say, blue light on an object, and it normally reflects red light, it's going to absorb that blue light. It's not going to reflect any light. That will then appear black to us. And then the other thing we were talking about was just for a transparent object, we talk about what's called selective transmission. And that is just the color of a transparent object is the color of light that it transmits through. The very last thing we were looking at is mixing colored lights. So one, our sun is actually white. And I'll talk about this more today. It looks yellow or red because of the light passing through our atmosphere. So our sun is actually emitting white light. But it's not emitting light equally in all frequencies. It tends to emit more light in the green-yellow part of the spectrum. Well, the way our eyes see, remember, is that we have these light sensors called cones in our eyes, and we actually have 3 different kinds of cones. And those are cones that are sensitive to low frequencies, cones that are sensitive to middle frequencies, and cones that are sensitive to high frequencies. And when all 3 of our cones are stimulated equally, that's when we see white. So in terms of color math, first sort of color math equation is red plus green plus blue in equal amounts equal white. Well, here's the cool thing. You can actually add red plus green plus blue in varying amounts and produce any other possible color. Because of this, they're called the additive primary colors. And if you look at your computer monitor with a really nice magnifying glass, you would see that all of these amazing colors are just being produced by 3 different pixels added together in different amounts. And the last thing we're looking at is adding specific colors together to produce other colors. So if I add red and blue in equal amounts, red plus blue equals magenta. If I add red and green in equal amounts, red plus green equals yellow. And if I add blue and green in equal amounts, blue plus green equals cyan. Well, that was sort of the last thing I talked about. What I want to do is just cover this in a little bit more detail, show you a couple of cool little animations, do some clicker questions, and then move on. Okay, so one, if I add 2 colors together to produce white, those 2 colors are called complementary colors. So 2 colors when added together produce white. So if I wanted to know, let's say, what is the complementary color of green? So I want green plus something is going to equal white. Well, I know that red plus green plus blue equals white. So if I wanted to add another color together with white, or with green to produce white, well, I already have green. So if I were to add red plus blue together, red plus blue plus green equals white. Well, red plus blue is really just magenta. So magenta is the complementary color of green. Because if I add magenta, which is a combination of red plus blue, and I add green to it, I get white. So going through that again, how about blue? What do I need to add to blue to get to white? Well, red plus green plus blue equals white. Red plus green equals yellow. And so red plus green plus blue is white. Yellow is considered the complementary color of blue. And then one last one, red. What do I need to add to red to get white? Well, if I add blue plus green plus red equals white. And so cyan plus red equals white. So 2 colors when added together produce white are called complementary colors. They're also considered opposites of each other. So a color plus its opposite equals white. So let me do a new share real quick and not. Okay, so just kind of going through all this. This is a cool little animation written by John, our lab tech. So what's showing here is colors that I produce in the middle are a result of adding different amounts of red plus green plus blue. This color matching game is you trying to figure out how to add all these colors together to produce the background color. But let's not worry about that. So if I take red and green together, equal amounts of red plus green produce yellow. And if I looked at a yellow section of a computer monitor, what I would see is it's not yellow light being emitted by the computer. Thousands and billions of little pixels. So what's producing yellow is the red pixels added together to green pixels. There is no blue in there. So red plus green together equals yellow. Red plus blue equals magenta. So if there was a magenta part of your computer screen and you looked at it closely, you would see it's just red pixels and blue pixels added together in equal amounts. Blue plus green is cyan. Again, equal amounts of blue plus green is cyan. And then if I add all three together, red plus green plus blue equals white. And then if no pixels were being illuminated, that's when we would see black. So again, sort of putting it all together, color vision, no, oh, let me do one more. Hold on one second. Animations. Oh, we were just doing that one. Spotlights. Okay. So again, if I take red, add it to green, equal amounts of red plus green equals yellow. I take blue, add it to red, equal amounts of red plus blue is magenta. I take blue, add it to green, equal amounts of red and green is cyan. And then when they all add together is when I get white. Okay. So let me just pause. I'm going to ask you a few clicker questions, but before I do, I want to just open it up, see if there's any questions about sort of the recap, what I've covered so far. No questions? All right. Recap going off. Let's do a clicker question or two. Okay, I'm going to try and do these as polls again. If you can't see the poll for some reason, don't worry about it. If you're on an iPhone, you may not be able to see it. So let's do a little poll here. Where's the polls? Oh, okay. Launch polling. So I'm going to take a look at question 27.3. It says the worst thing you can do for the health of a green-leafed plant is to illuminate it with only red light, green light, blue light. All are equally naughty. I didn't write that. Or none of the above. What do you think? If I had a green-leafed plant and I shined different frequencies of light on it, different colors, which one would be the worst for the health of a green-leafed plant? What do you think? Take a second. Do you see the poll? Put in an answer, completely anonymous. We got a couple people say B, a couple people say D. One person says D. Gonna give you another 10 seconds if you want to throw in a vote. What do you think? Our answers right now, we got A, B, D. Okay. Let me end this polling and share it, share the results. We've got a tie between B and D. So one, if it's a green-leafed plant, that means it is absorbing other frequencies of light except green. Green is what's getting reflected back. You probably know that a plant needs light to survive. So if I only shined green light on a green-leafed plant, it is going to reflect that light back to us. None of it is going to get absorbed by the plant, so that plant is going to die. So color of an opaque object is the color of light it reflects. A green-leafed plant is green because it's reflecting green light back to us, absorbing the other frequencies. So if you only shine green light on it, then it's only going to reflect the light that you shine on it. None of it's going to get absorbed. Bad news for the plant. So the correct answer was B. You do not want to only shine green light on a green-leafed plant because it will not absorb any of that light. Okay, let's do another one. Just real quick, touching on 27.4, which will warm up quicker in sunlight, a piece of colored glass, piece of clear glass, or both? A red piece of glass is red because it's letting red light go through it. A transparent object is the same as the color of light it transmits. So a clear piece of glass will transmit all frequencies of light through it. It will not absorb any light, so it will not heat up. A piece of colored glass is going to absorb certain frequencies and only let others pass through it. That means it is absorbing some light, therefore it's absorbing the energy the light had. So a piece of colored glass would warm up quicker in sunlight. Okay, 27.5 is a good one. And you may see something like this again in some form on a quiz, celebration, and so on. So let's relaunch this. And the question is 27.5. A sheet of red paper will look black when illuminated with red, yellow, magenta, cyan, or none of these. So I have a sheet of red paper, which means it would normally reflect red light. How could I make that piece of red paper look black? By shining red light, yellow, magenta, cyan, or none of the above. What do you think? Take a guess, throw in an answer if you like. How could I make a sheet of red paper look black? By illuminating it with red, yellow, magenta, cyan, or none of the above. Take 5 more seconds. Okay, going to end this polling. Share the results. We've got a majority say D. Red paper will look black when illuminated with cyan light. So if a red paper is going to look red, it has to have red light to reflect. So one, I shine red light on it, it's definitely going to appear red because it can reflect the red light. Well, what is yellow though? Yellow is really a combination of red plus green, which means there is a red component to yellow light. So if I shine yellow light on an object, it can reflect that red light. It'll absorb the green, but it will appear red. Magenta. Magenta is a combination of red plus blue. There is red light for it to reflect, so it would appear red. On the other hand, cyan is a combination of blue plus green. There is no red component of cyan light. So if I shine cyan on a color, on an object that would reflect red light, it's absorbing all of it. There is no red light for it to reflect, so it would appear black. One more. And again, expect to see something like this in the near future. If I took white light and I subtracted off green light, what would the result be? And let's do this one more time as a poll. So this is question 27.6. And it's the following. I take white light and I subtract off green light. What am I left with? Red, green, magenta, cyan, or yellow? What do you think? Take 30 seconds, throw in an answer once you have one. All right, gonna give you 10 more seconds if anybody else wants to go. Right now, C is the winner so far. Anybody else? Going once, going twice. Sold for no dollars. We've got 50% of you say C, magenta light. So here's how you do a problem like this, and you will have something like this in the near future. So white is really a combination of red plus green plus blue. So if I take red plus green plus blue, which is white light, and I subtract off the green, what I'm basically left with is red plus blue. Red plus blue is magenta. And so if I take white light and I subtract off green light from it, what I'm left with is the combination of red plus blue, which equals magenta. So let me just show you this as a little animation. It's kind of cool. Let's do interactive stage lighting. Where's the person? Let's do white light. Okay, so let's say I had a blueberry, a blue person. The only way that that object is going to appear blue is if there's blue light for it to reflect. So I shine white light on it. White light consists of all frequencies. There is a blue component for it to reflect. Before I show you this, take a second and think about this. How many of these other forms of light, if I shine it on a blue object, would make the object appear blue? So right now, if I shine white light on it, obviously there's blue for it to reflect. If I had black light or no light, obviously it can't reflect. But what about red, green, yellow, blue, magenta, and cyan? How many of those will, actually, I could do this as a poll too. Ooh, let's try this. Relaunch polling. So instead of A, B, C, D, and E, think about 1, 2, 3, 4, 5. So red, green, yellow, blue, magenta, cyan. Out of those 6 colors, how many of them would make this blue object appear blue when I shine light on it? Would red light make it appear blue? Would magenta light make it appear blue, and so on? What do you think? We got 4. So if you think the answer is 1, put A. Think the answer is 2, put B. 3, put C. 4, put D. And then we will go through it in 15 seconds. So again, if it's going to appear blue, whatever light shining on it has to have sort of a blue component to it. White has all colors mixed together, so anytime I shine white light on an object, it'll appear whatever color that it reflects. All right, let me just end this so we can move on. We've got C being the majority, 3 of these colors. All right, so let's look. I shine red light on this, it's going to appear blue. I'm sorry, appear black. Why? There is no component of blue. I shine green light on it, it's going to appear black because there's no blue light to reflect. How about yellow? Well, yellow is a combination of red plus green, so if the object's blue, there's no blue light for it to reflect, it'll appear black. Obviously, if I shine blue on it, it's going to appear blue. How about magenta? Well, magenta is a combination of red plus blue, which means there is blue light for it to reflect, so it'll appear blue. And then how about cyan? Cyan is blue plus green. There is a blue component for it to reflect. So let me stop that and just open it up real quick to see if there's any questions on that. Keep in mind, color of an opaque object is the same as the color of light it reflects. If I have a blue object, it can only appear blue if there's blue light shining on it that it can reflect, or some component of blue light. So I shine white light on a blue object, it can reflect the blue component of white light. I shine magenta light on it, it can reflect the blue component of magenta light.
I have a question about one of the clicker questions that you kind of went over fast. It was I think it was the second one we did, the one with the which glass would warm faster. Can you explain again?
Which will warm up quicker in sunlight? A piece of colored glass, a piece of clear glass, or both? Or both will warm up the same. So glass is transparent, which means it lets light pass through it. A blue piece of glass is blue because it's letting blue light pass through it, absorbing the other colors. A clear piece of glass will let all frequencies of light pass through it. So anytime an object absorbs any amount of light, it's going to heat up a bit. So a piece of colored glass will heat up more than a piece of clear glass because the clear glass will let all of the light pass through it. The colored glass is going to let all of the light pass through it except, well, it's going to absorb all of the light except whatever color it is. So blue glass would let all colors of light, keep doing that. Blue glass is letting blue light pass through it. It's absorbing all the other frequencies of light. Anytime it's absorbing light, it's going to absorb the energy that that light had. So a red piece of glass will let red pass through it, absorb all the other frequencies, but a clear piece of glass is going to let all frequencies of light pass through it. Does that answer your question?
Yeah, thank you.
All right. So I want to just any other questions before I move on? It's kind of a long recap, but okay. I want to just quickly touch on color subtraction. Okay, so let me actually just show this PowerPoint. So, here's our additive primary colors. And I mentioned this before, but there's a difference between adding colored lights and adding colored pigments. So if I were to take a red crayon and a green crayon and put them both on a piece of paper at the same time, I am most definitely not producing yellow. There's a difference between how you add colors together in terms of light and then how you add colors together in terms of pigments and things like that. Just skip that. So subtractive primary colors. If you think about it, how do all magazines and things like that work? You've got white light shining on a magazine. The little pigments in the ink are going to absorb certain frequencies of light, reflect the others. We call it subtractive primary colors because all a pigment can really do is take white light, which is shining on it, subtract off some of those frequencies by absorbing them, and then reflecting the others. So if you ever buy ink for your printer, you do not buy red, green, and blue ink. What you buy are magenta, cyan, yellow, and then black. And if you have a good printer, sometimes you even have two different blacks, one for printing photographs and pictures, another one for printing text. So if you take a nice magnifying glass and you look at any kind of color magazine, instead of pixels, which you'll see are millions and millions and billions of little dots, and those dots are either magenta, cyan, yellow, or black. And when you add them together, you produce different colors. So for magazines, for printers, anytime you're looking at a magazine, it's really just a result of cyan, yellow, magenta, and then plus black. And I'm not going to go into the rules for color subtraction, but, well, let me just touch on one. You can kind of see here that if I were to take magenta plus yellow, I would get red. And I'm getting that just from looking at this. So if I take magenta here and add yellow to it, the end result is red. Why is that? And again, this is just sort of a little extra piece. You don't know it, but I just want to kind of go through it because it's interesting. Well, keep in mind, I'm shining white lights on, let's say, a magazine. And white light is really a combination of red plus green plus blue. And if I have something that's magenta, what is magenta? Well, magenta is really a combination of red plus blue. Well, how do I get magenta from white light? Well, if I take white light and I subtract off green, the end result is red plus blue, which is magenta. So a dye, a pigment that's magenta, is really subtracting off green light. So I've got white light shining on a pigment that's magenta. What is that white, or what is that pigment doing? It's subtracting off the green light. So it's absorbing the green light, and then it's reflecting back the red plus blue, which is magenta. So when I have magenta over here, what I'm really doing is subtracting off the green light. Now, how about yellow? Well, yellow is a combination of red plus green. So if I take white light and I subtract off blue, what I get is yellow. So a yellow pigment is one that is absorbing blue light, reflecting back the green and the red. So if I have a combination of magenta and yellow, a magenta pigment is subtracting off all the green. A yellow pigment is subtracting off all the blue. Well, what happens if I take white light and I subtract off all the green and I subtract off all the blue? What I'm left with is red. So you don't need to know this, but magenta plus yellow equals red for that reason. It's that magenta is subtracting off all the green light from white light. Yellow is subtracting off all the blue light from white light. And when I subtract off all the green and all the blue, what I'm left with is red. Okay, so again, you don't need to know that, but I just wanted to mention that there's a complete difference between mixing colored pigments like paints or dyes and mixing colored lights. So again, pigments, they're just teeny tiny particles that are designed to absorb specific frequencies of light or specific colors. So when you're looking at a magazine, it's not emitting its own light. It's taking white light, absorbing some of those frequencies of white light, reflecting the rest. We call it color subtraction because I'm taking white light and subtracting off specific colors from it. So magenta, cyan, and yellow are called the subtractive primary colors. And anytime you look at a painting or photograph, you pretty much just have thousands of little dots being added together, just like pixels of light. And those dots are magenta, cyan, yellow, and black. Booyah. Okay. I've got a half hour. Well, it's supposed to end 10:15. I'll probably get a little bit over. So last things I want to talk about are, why is the sky blue? Why are sunsets red? Why are clouds white? And let me emphasize something to begin with. Our sun is white. It only appears yellow because the light passing through our atmosphere is affected by our atmosphere. But if you could go out into space, if you could see the sun from the moon, it does not look yellow. Our sun is emitting light of all frequencies. Our sun is actually white. So actually, before I go into all that, let me just pause for a second. Any quick questions about color subtraction or the beginning statement that our sun is not yellow? Our sun is actually a white sun. And I'm going to go through in a little bit, but the colors of our sun at sunset, at noon, all depend upon what makes up our atmosphere. If we didn't have nitrogen and oxygen in our atmosphere, our sun would look a different color, our sky would look a different color. Okay, let's jump into this. So why is the sky blue? Well, remember, how does light get through a transparent material like glass? By constantly getting absorbed, re-emitted, absorbed, re-emitted, absorbed, re-emitted, millions and billions of times until it makes it all the way through the glass. Well, our atmosphere is no different. Our atmosphere is a gas rather than a solid like a piece of glass, but the way light gets through our atmosphere is by constantly getting absorbed and re-emitted by the atoms and molecules that make up our atmosphere. So first point, atoms and molecules in the atmosphere re-emit light that shines on them. They basically absorb it and then re-emit it. Here's the thing that's different about a gas than a solid. Going back to our example of, let's say, a piece of glass. You've got, this piece of light going through. It's getting absorbed, re-emitted, many, many, many times, but that light is getting re-emitted in the same direction it was traveling. It passes through the glass. Well, when an atom or molecule of gas in our atmosphere absorbs light and then re-emits it, what it does is it doesn't re-emit it in the same direction it was moving. It re-emits it in all different directions. It's called scattering. So the light is scattered, which means it's re-emitted in all directions. So let's say here's a piece of sunlight coming in, and here's an atom of nitrogen or oxygen in our atmosphere. This atom will absorb this incoming light. That light will be completely gone. But then when it re-emits it, it doesn't re-emit it in the same direction it was going. it re-emits it in many different directions. So this scattered light is going to be weaker than the incident light because it's going to be emitted in many different directions. So this might be one piece of sunlight coming in, it gets absorbed by this atom, and then this atom re-emits that light, but it re-emits it in many different directions. It re-emits weaker light in many different directions. So this incident light that's coming in gets absorbed and then re-emitted in all directions, and that's what we call scattering. Well, here's the thing. Even though atoms in our atmosphere will re-emit light that shines on them, it doesn't re-emit all frequencies of light equally. Here's the big thing to keep in mind. The smaller an atom or particle is, the better it's going to be at re-emitting high frequency light. So small particles, they scatter high frequency light. Heavier particles or big particles, they will tend to scatter low frequency light. Meaning they scatter certain frequencies of light better than others. The smaller a particle is, the better it will be at scattering high frequency light. Well, nitrogen and oxygen are the main things in our atmosphere. Our atmosphere is about 78% nitrogen, about 21% oxygen. Those are relatively small particles. In terms of, if you look at our periodic table, these are pretty small overall. Well, small particles tend to scatter high frequency light better than any other frequency. So it ends up that in our atmosphere, nitrogen and oxygen scatter violet the most, followed by the other colors in sort of decreasing order. So remember, our spectrum is red, orange, yellow, green, blue, indigo, violet. These are the high frequencies. Blue, indigo, violet. Red, orange, yellow are low frequencies. So our atmosphere is mostly nitrogen and oxygen. They tend to scatter, meaning they absorb white light from the sun, and then they re-emit it in all directions. But they preferentially re-emit high frequency light. And just to give you a number, it ends up that red gets scattered about 1/10 as much as violet. So white light comes in from the sun, nitrogen and oxygen absorb it, and then they re-emit it in all directions. But nitrogen and oxygen is going to preferentially re-emit high frequency light better than any other frequency. So what we are seeing in our sky is the re-emitted light by whatever is making up our atmosphere. So the reason our sky is blue is simply because we're seeing the blue light scattered by our atmosphere. Now, technically, violet is scattered more than blue, but our human eyes are not as sensitive to violet as they are to blue. If they were, we would see more of a violet sky. So violet is scattered the most, but our eyes are not as sensitive to violet as they are to blue. So we see more of a blue sky. So big point, and just write this here. On a planet, the color of the sky is the color of the light best scattered by the atmosphere. So the only reason our sky is blue is because nitrogen and oxygen in our atmosphere scatter blue light better than any other light. Now, one thing is kind of interesting if you ever thought about this. So let's say here's the Earth. Woo! And this is you. You're on top of the world. Hey. And you're looking this way. Well, if the sun is over here, keep in mind, if you're going to see something, light from that object has to enter your eye, either by emitting its own light or light is getting reflected or scattered from something else. So if I have the sun, which is behind me, none of the rays from the sun would actually enter my eye unless there was something in the atmosphere emitting or absorbing it and then re-emitting it. So how is it when I'm looking out this way that I can still see a blue sky? And that's because I have atoms of nitrogen and oxygen in our atmosphere that take this incoming light, they absorb it, and then they re-emit it in all directions. So this might be one atom of oxygen or nitrogen, which is then absorbing the white light from the sun and then scattering it in different directions. So when I'm looking in a direction that's not looking at the sun, I'm not seeing light directly from the sun. I'm seeing light that got absorbed and then re-emitted many times by all these little molecules of nitrogen and oxygen in the atmosphere. So when I'm looking in this direction opposite the sun, I see blue light because there's little atoms of oxygen and nitrogen that took the white light from the sun, absorbed it, and then re-emitted it in different directions. Some of that re-emitted light made it back to me. Let me pause that for a second. If you understand that, then you'll really get why sunsets are red, which I'm going to cover next. So our sun is a white sun. It's emitting light of all frequencies. Haven't gotten to why it appears yellow and red yet, but our atmosphere is made of oxygen and nitrogen. It tends to scatter high frequency light better than any other color. The color of a sky on a planet is just the color of light that gets best scattered by whatever makes up the atmosphere on that planet. On the Earth, oxygen and nitrogen tend to scatter blue and violet better than any other frequency. So that's the color that our sky appears. It doesn't look violet because we're not as sensitive to violet light as we are to blue light. So let me pause, just open up questions for 30 seconds about anything about that. So white light from the sun gets absorbed by atoms in our atmosphere, but then it re-emits it in all different directions, not just the direction it was going. Tends to re-emit, scatter violet and blue best. Okay. So our atmosphere is also the reason why our sun doesn't look white. So going along this real quick, if I were to look at the position of the sun at noon and at sunset. So here's you. Woo. And here's our atmosphere.
Joe, I don't think you're doing a screen share right now.
Oh, I don't think I am either. Thank you for that. Screen share. Okay, so let me actually just do this again. Okay, so here is the Earth. Here is you. And let's give our atmosphere a blue atmosphere, blue. So I've got all of this bazillions and bazillions and bazillions and bazillions and bazillions of oxygen and nitrogen molecules. And let's draw a yellow sun. We'll just make it a red sun. At noon, the sun is directly overhead. So this is the sun at noon. At noon, light from the sun has to pass through the least amount of atmosphere at any time. At sunset, the sun is over here, let's say. So this is the sun at sunset. Well, what ends up happening is the light at sunset to get to us has to pass through a lot more atmosphere than when it's overhead. Keep in mind the sun is emitting white light, and what our atmosphere is doing is scattering away the high frequency light. That's why our sky appears blue, is just from the scattered blue light. Well, what happens if I take white light and I get rid of some high frequency light? Well, remember, our high frequency light is sort of blue, indigo, violet, and our spectrum is Roy G. Biv. Well, if I take white light, which consists of all frequencies of light, and I get rid of some of the high frequency, not all of it, but some of it, then the end result is our sun appears more of a yellow shade. So you've got white light coming in from the sun. Our atmosphere is scattering away a lot of the high frequency light. Well, if I take white and get rid of some high frequency, I'm left with more of a yellow color. But at sunset, the light has to travel through much more atmosphere than it does at noon. If I take white light and I get rid of all the high frequency, so white light minus all high frequency light, that's when I get to see red. So the difference in the color of the sun at noon and at sunset is just because the light from the sun, which is white, has to pass through more atmosphere at sunset. The whole time the light is passing through our atmosphere, that high frequency light is getting scattered in different directions. Well, at noon, and let me just go back to these lecture notes and do it. Okay, so let's say, you're sitting over here and you're right there. And our atmosphere is about 20 miles thick. Remember, it gets thinner and thinner and less dense as you go higher up, but our atmosphere extends up many, many, many miles. So at noon, the sun is right overhead. The light travels through the least amount of atmosphere. Some of the high frequency light is scattered, but not all of it. So if I take white light and get rid of some of the high frequency light, that's going to look more of a yellowish color. However, at sunset, as the sun is setting, now it has to pass through a lot more atmosphere to get to us. It travels through the most atmosphere it can. All the high frequency light gets scattered away. If I take white light and I get rid of all the high frequency light, what I'm left with is more of a reddish orange color. So sunsets are red because the light from the sun travels many, many, many miles through our atmosphere. All of the high frequency light gets scattered away, and what we are left with is reddish light. So let me just see, there was a chat. Let me see if I can pull that up. Tab. Let me just stop this for a second. Thanks, Joe. Oh, okay, thank you. So, sun is red at sunset. Sun is yellow at noon for the same reason. And that's because the white light from our sun has to pass through our atmosphere. Our particular atmosphere of nitrogen and oxygen preferentially scatter the high frequency light. The color of our sky is the color of light that gets scattered by nitrogen and oxygen, which is blue-violet. Violet gets scattered the most, but we're not as sensitive to it. At noon, the sun's overhead. I take white light, and as it's passing through the atmosphere, I'm getting rid of most of the high frequency light, but not all of it. White minus some high frequency light is yellow. During sunsets, the light has to travel through much, much, much more atmosphere. All the high frequency light gets scattered away. When I take white light and I remove all the high frequency light, that's when I have more of a reddish orange color. So let me just pause for a second and see if I can answer any questions about that. Okay, couple other points while I'm here. Sunsets are often more beautiful than sunrises. Why is that? And actually, just let me just say, with this whole COVID thing, it's becoming less of a difference. But during the day, with all these cars running and factories running and things like that, all of this pollutant gets into the atmosphere. Well, if I have things other than nitrogen and oxygen scattering light, they may scatter different frequencies of light than oxygen and nitrogen do. So oftentimes a really beautiful, colorful sunset, unfortunately, is the result of lots of pollutants and shit and crap that's in our atmosphere. Well, over the course of the night, a lot of that stuff sort of dissipates away. And so our atmosphere is generally clearer, more clean during the day. And so because of that, sunrises tend to be less spectacular and less colorful than sunsets. And that's really just because of pollution. I don't know if you remember this, but Mount St. Helens, which was a volcano that exploded, God, I don't remember, like 30 years ago or something. Sunsets after that around the volcano were spectacular for months and months and months after that, because all of this crap got sent up into the air. Because of that, it scattered different frequencies that were normally it scattered different frequencies of light that were normally not scattered. And so because of that, you could get these colorful sunsets that you wouldn't normally get if our atmosphere was clean and didn't have any kind of pollutants and stuff like that in it. Okay, very last thing. Why are clouds white? And not even just why are clouds white. Have you ever thought about this? And I think it's one of your homework questions. You get a root beer, or hell, Santa Cruz, just a beer. The beer is yellowish, brownish, but the foam is white. Why is the foam a different color than the beer? What's suddenly causing it to change color? Or if you go to the ocean and the waves, as the waves are breaking, the white caps, they're called white caps because they're white. Why are they suddenly white? Well, keep in mind, water, clouds, things like that, they're not emitting their own light, right? It's not a light source. So something either emits its own light, like a light bulb or the sun, or it reflects light shined upon it. It reflects light shining on it. So clouds are not emitting their own light. They're scattering sunlight. Well, what is a cloud? Well, a cloud is really just water droplets of many, many, many different sizes. And remembering that things in our atmosphere will scatter different frequencies of light. Large droplets, well, we were talking about small droplets, small atoms and molecules tend to scatter high frequencies. Large droplets tend to scatter low frequencies like red, and medium droplets tend to scatter mid frequencies like green and yellow. Anytime I see all frequencies of light at the same time, that's when I see white. And so the reason clouds are white is because you've got light from the sun coming in. The cloud is made up of many, many different kinds of particle sizes of water droplets. Those teeny tiny water droplets are going to scatter the high frequencies of light. The bigger droplets are going to scatter the lower frequencies of light, and the middle droplets are going to scatter the middle frequencies. And anytime all frequencies are present is when we see white. So that's the same thing with like the foam of a beer or a root beer. Even though the root beer might be a brownish color, the foam is sort of root beer atoms and molecules of many, many different sizes. The different sizes scatter different frequencies, and that's why we see the foam being a different color than the rest of the root beer. Okay, there's one question that I wanted to ask as a clicker question. That's sort of the last new piece, and then I'll just see if there's any questions. So I mentioned the color of the sun, the color of the atmosphere, the color of sunsets and sunrises has to do with whatever's making up the atmosphere on that planet. So the question here, again, let's do this as a poll for the few of you left. Relaunch polling, continues. So for this question is, if the sky on a certain planet in the solar system were normally orange, what color would sunsets be? So our sky, blue, we have a certain color sunset. But let's say that on a different planet, in the solar system or somewhere else, let's say the color of the sky was orange. If that's the case, what color would you expect sunsets to be? What do you think? Take a minute, throw in a vote. Roy G. Biv. What do you think? If the sky on another planet was orange, what color would the sunsets be? And just for timing, we will just end this now. Got 2 people. 3 people. Woohoo! Share the results. We've got B, C, and D. So 2 things to keep in mind. Color of the sky is the same as the color of light that's scattered the best by the atmosphere. So if the sky on a certain planet was orange, then that would tell me that, one, remember this is low frequency, and my blue, indigo, and violet is sort of my high frequency. If the sky appears orange, that means that atmosphere scatters low frequency light best. Scatters low frequency light best. Well, during sunset, the sunlight has to pass through the most atmosphere. If I take white light and I get rid of all of the low frequency light, what's going to be left is the higher frequencies of light. So if a sky appeared orange, that would tell you that that particular sky, whatever makes up it, is scattering low frequency light more than high frequency light, which would mean it's made up of bigger atoms. So what's left over at sunset would be what's on the other end of the spectrum. So if I take white light and I get rid of all of the low frequency light, I'm going to be left with sort of a more bluish violet sky. Or bluish violet sun, which would be pretty damn cool. All right. Well, that is chapter 27 in a nutshell. So all about color. Chapter 27 homework is due tomorrow by 11:59, and then quiz on chapter 27 due on Saturday. Just like before, it's a 10-question multiple choice test. I think you have a half hour, plenty of time. And then after this, we're just covering one more chapter, chapter 28, on reflection and refraction. So I'm going to end lecture portion. Bring in office hours. If anybody has any questions about anything I just covered, let me know. If not, thank you all for joining me live. I hope you have a wonderful rest of the day and an awesome weekend.
Thank you. Have a good weekend.
Thanks, Laura. Take care. Have a good weekend.
Yeah.
Thank you.
You done? Any questions for you, Allie?
Oops.
Nope.
Nope, I'm heading out now.
All right. Take care. Have a good weekend.
Thank you. You too.
All right. Bye-bye.